There, this is Stan Forster, and I'm going to show you a few details of the refracting or bending light simulation from the University of Colorado. Okay, so we have our welcome screen here. I'm going to go ahead and I want to start her up. Let's see, do they have? Okay, so they got prisms and more tools. So we have the introduction here. Okay, and then we can just play around with this. Notice that you have a refracted beam and a reflected beam. And notice how the intensity of the two changes. When we're at something like this, that light has a very small angle of incidence. In other words, that angle between this and surface normal means perpendicular to the surface. Okay, surface normal and the incident light is very small, and it's basically the photons are punching their way through. Now, that's going to happen more and more as the higher and higher frequency goes. If we ever get up to um, X-rays. X-rays. You can't use regular mirrors for X-rays. Try to focus them. I understood. That's not the point of today's lab, but just a little background material for understanding light waves. Okay. So notice here that the amplitude gets darker. More and more of the waves are actually reflected than refracted. Okay. And so when we're dealing with gamma rays and X-rays, and if you want to actually focus them, like say in an orbital telescope that's an X-ray observatory or gamma ray observatory, you have to focus those beams with a very large angle of incidence. We call this grazing incidence. They basically ricochet off the surface. Okay, let's see what this looks like. We're going to go to waves. You can see the waves here. Okay, and you can see that the speed of the waves is different. The speed of the waves is the same in for the reflected wave because it's in the same medium. Okay, the speed of the waves in the new medium, because it's denser, has a higher index of refraction. Uh, the speed of the wave is much smaller. Right. So let's go ahead. Let's go back to Ray, and let's go backward here. Let's see if we can start the next one here. Okay, we've got our prisms here. Let's start with this one here. This one might be familiar to you um, from your non-lab course, from the lecture course. Notice here that we can refract that light out. Now, what happens if I change this to a higher wavelength? Is it possible to change this to a higher wavelength so that we undergo something called total internal reflection? Okay, we get total internal reflection here. In other words, as okay, so as that incident angle gets smaller and smaller, or excuse me, greater and greater, more and more of uh, the refracted angle gets a little closer to the normal, and then comes out even closer and closer to this far surface. Now, if we come down like this, there comes a point in which we go any further. Notice how light this is. We're getting less and less of the light out and more of the reflection. We're not seeing the reflection just yet. Okay, but as that angle gets closer and closer, eventually you get to the point where Snell's law, we're actually taking the sine of 90 degrees, which is zero. And so nothing is getting refracted out of this surface here because the angle of incidence is so great. And then what we're having here is internal reflection. It comes to this surface here, and then you would draw a surface normal there. You would take your angle of incidence, and you'd figure out what your angle of refraction is. But if we were at the same time were to go back to red light, because the index of refraction is different at the two different wavelengths, we can still get refraction out of the second surface rather than um, reflections. Let's see what we got here. Let me come back over here. Let's see the simulate. Yeah, simulation shows your surface normals here. So let's take advantage of that. And then we're going to go back. We'll see the last one. Oops. Okay, here's your more tools. All right, now we have two different media here. Again, we have the reflection and refraction. We can take this here. We can start measuring angles. Okay, if we have 30 degrees, our reflected angle is again, maybe I got that wrong. Okay. Okay, my incident angle is 30 degrees, 0 to 30. My reflected angle is exactly the same. Notice we're going into something with a higher index of refraction, 1.50. That's glass. So it's going to come down over here. If that angle is going to be less, you go into a more dense material, your refracted angle is going to be less. What if we were to change this around? Let's make this glass. Let's make that glass, and let's make this air. Aha. So we got 30 degrees incident angle. We still have a reflected angle at 30 degrees. Remember, these waves are going to yeah, got to reboot English. Reflect and refract. Okay. But now we're going into a less dense material, a material that has a lower index of refraction. And so your angle between your surface normal and your ray is going to be even greater. Okay. So just play around with that. If you have any questions, please post them. I need to stop recording so you guys can see this video. Okay, now how am I going to do this?